Okay, geometry students, these are your notes for Thursday evening for Friday the 4th class. This will be the last notes that we take going towards the Unit 2 test, which I think will be next Wednesday or possibly Tuesday sometime. Anyway, tonight we're working on dilations in the Cartesian coordinate plane, so our objective is the student will learn to apply dilations to objects in the Cartesian coordinate plane. Again, these are the notes for Friday, October the 4th. Out of the 4 transformations, this will easily be the hardest of the 4. There's not much of a system to it. You're simply going to have to apply some brain cells and figure out how the dilation is going to work. So let's get started. Okay, basic background information again. The Cartesian coordinate plane, that's our fancy name for the XY graph that you've been working on for years. Ordered pair precisely locates any object in the CCP. Okay, we have our 2 values, the abscissa and the ordinate. We will not really be working with the abscissa and the ordinate as far as switching them like we have been with some of the other stuff like rotations. Okay, so anyway, as we look at our pre-image has corner points that are capital letters, and our images have prime markers on them. And of course, as we transform figures over and over again, they go from single prime to double prime to triple prime and so on. Okay, now for dilations, we're going to need a little bit of information and a few ideas to file away in the back of our heads. Okay, so if I go too fast, of course, hit pause and then press play when you're ready to begin again. We're going to need to know, just like we did with the regular dilations that were not in the CCP, we're going to need to know a scale factor. Okay, the scale factor, remember, is a ratio that tells us how a figure enlarges or reduces as we move from the pre-image to the image. And it also tells us by how much it enlarges or reduces from the pre-image to the image. Okay, we will also need a point of reference that the dilation is going to happen with. As you will see in the examples, sometimes that will mean moving a certain point to a particular location like the origin, or maybe just a particular coordinate in the graph, or sometimes it will mean maybe the entire figure is trying to fade away into a location like the origin, and we'll look at one of those as well. Other information that you're going to see, if you've kind of been wondering how come we stuck all of that distance formula and midpoint formula and slope and all that, why we did that in the middle of a chapter or a unit that was dealing largely with transformations, well, you're going to see why. Okay, the idea of midpoint and distance and slope is very much in play with dilations in the Cartesian coordinate plane. Okay, so you're going to see a real close relationship between these 3 measurements as we move forward. Okay, the first example that we're going to look at is we are instructed to take this triangle and we're going to dilate triangle ABC with a 2-to-1 scale factor so that the figure converges into the origin. Okay, now let's look at that scale factor for a second. Let's make sure we remember how to read it. It says 2-to-1. That is communicating not only by how much the figure will grow or shrink, but also whether it will grow or shrink. Now you read the scale factor from left to right, if it's in colon notation like this one is, or if it happens to be a fraction, you read it from top to bottom, numerator to denominator. 2-to-1. 2, the very first number on the left, that represents our pre-image, and the 1 over on the right represents the image. So as we move from the pre-image to the image, the size of the figure is going from 2 units tall down to 1 unit tall. So this will be a reduction. Our image will be smaller. Okay. Now, it says that it converges into the origin. What that simply means is all of the corner points are simply moving in a direct line towards the origin. So the figure will get smaller and smaller as these points move along those dotted lines until ultimately they all converge on each other as they hit the origin. Okay, so there are several things that we're going to look at here. Okay, obviously we have information like our original points. Okay, and we know that all of these points are going to the origin. So that's where your left 2 columns are looking at there. You have your coordinates for A, B, and C, and they are all going to 0, 0. Okay, well, we're going to apply a simple concept, which is slope. We're going to figure out, as point A moves towards the origin, what is the slope of the line that it is moving along? And then we will repeat that for B and for C. Well, let's take a look at the line that connects point A to the origin. What is its slope? How much is its rise and its run? Okay, well, obviously its rise has to come down 2 units, and it would have to run 6 units in order to reach the origin. So its slope is down 2 over 6. Okay, but we're actually only going to move point A halfway to the origin. Why halfway? Because our new figure is trying to be half as big as the original figure. Moving it halfway to the origin should collapse its size by half as much. Okay, so if it slopes by -2 over 6 to get all the way to the origin, then what would be the slope to get halfway to the origin? We wouldn't want to go down 2, but we could only go down 1. Okay, we wouldn't necessarily need to run 6 units, but running halfway would be 3. So halfway to the origin would be a slope of -1 over 3. So if we move from point A by way of slope -1, +3, what coordinate would that put it at? Down 1 unit over 3 units would put point A at -3, 1. That is halfway to the origin. Okay, so there's A prime. Now let's do the same for B. What would be the slope of B to get to the origin from where it is? Clearly it needs to come down 5, and it needs to move, it needs to run 4. So we're looking at a slope of -5/4. What would be half of that? Now, unfortunately, we cannot, when we do half of 5, we do not end up with a whole number, but that's okay. So we're going to come down 2.5 and run 2. Okay, so if we come down 2.5 units and run 2 units, what is the coordinate of B prime? Okay, it's going to be at -2, 2.5. Okay, so point B has moved halfway to the origin as well. Point C, how does C get to the origin? The slope would be down 3 over 1, so a -3 over 1. Halfway would be down 1.5 over 1/2. Okay, so where would that put point A at? It would put it at -1/2, +1.5. So point C has moved halfway to the origin. Now by connecting the dots, okay, we would end up with a graph, which I did not get a slide. Okay, but there would be triangle A prime, B prime, C prime. Uh-oh, sorry, let me get that off the screen. Oh, now I need to get that off the screen. There we go. Okay, so that's how this one works. All right, we'll look at another example. Okay, this time we're going to take the same triangle, triangle ABC, but this time we're going to dilate it by a scale factor of 1 to 2. And we are given instructions that the dilation is supposed to occur so that point A translates by way of x plus 4 and y minus 3. Okay, this is a typical dilation question. They're making us change the size of the figure, and they're also making us translate it as well. Okay, so let's read that scale factor, 1 to 2. What is this going to mean to the figure? Okay, the first number is 1. That belongs to the pre-image. The second number is 2. That belongs to the image. So we're going from a size of 1 to a size of 2. This is an enlargement. Okay, an enlargement. Now, point A is going to translate x plus 4. That simply means the x-axis is going to go up 4, and the y-axis is going to go down 3 from where it is. So if point A moves plus 4 towards the x-axis, down 3 on the y-axis, then we have the location of A prime. Okay, A prime is going to be at -2, -1. Okay, so we fulfilled the translation part of this, but now we need to dilate to the size that they say triangle ABC should be. Okay, so we're going to employ some of the same type thinking. Okay, we're going to look at it and go, okay, now the side of the triangle AB has a slope. Okay, and that slope basically tells us how do we move from point A to point B in the graph. Well, how do we move from A to B? We need to rise up 3 units and we need to run 2 units. So the slope of line AB is 3 to 2, 3 over 2. Okay, but we are now increasing the size of our figure by twice as big. Okay, so that means that we're going to have to rise twice as much. We're going to have to run twice as much. So 3 over 2 is going to become 6 over 4. Okay, now from point A prime, if we rise 6 units and run 4 units, we should end up with B prime. Okay, so rising 6 and running 4 would end us up at location 2, 5. Okay. Now let's look at the same type of idea for the slope of side AC. Okay, to get from point A to point C in that triangle, we need to slope a certain distance. Okay, so how much do we rise? How much do we run from point A to point C? We're going to rise up 1. We're going to run 5. Okay, but again, we're not trying to rise and run the same amount. We're trying to run twice as much. So up 1 over 5 is going to change to up 2 over 10. So from point A to get to point C, we should rise 2, we should run 10, and that would put us way out at 1, 8. Okay, but our 3 points are plotted. We can connect the dots, and we have our figure. It has been translated so that point A is right 4 and down 3. Okay, A prime is right 4 and down 3 from point A, and our triangle is now twice as big thanks to the slope formula. Now, if you get to thinking about it, okay, this idea can also be accomplished with a distance formula. We can find out how far it is from point A to point B, and then we can double that to figure out where point B prime should be at. Or, like with the previous example, instead of taking half of the slope, we could have used the idea of midpoint. We could have used the origin and the coordinates of the triangle ABC to figure out the midpoint, and that could have placed it there for us as well. So you can see that in the graph, the ideas of slope and midpoint and distance, they are all very interrelated. I've got one more example, but we will save it for class just to make sure that there are no questions, because this is a little bit more complicated than the other transformations that we've been doing. So let's go ahead and copy this guy down in your notes. Even those of you that have made it a habit to not be copying down the examples, which, by the way, is not working out very well. A lot of you are skipping the examples to make the notes shorter, but then when it comes time to do the activities in class, we don't seem to have much of an idea what we're doing. Okay, so copy down the example. We'll work this one out in class together on Friday, and then we will do our assignment. And again, we will have a test probably in the middle part of next week, so begin preparing yourself for that.